Hello, friends. This is Josh Price, and this is the Chapter 26 set of lectures on nucleic acid chemistry. Before we dive into nucleic acid chemistry, I need to do just a little bit of housekeeping because there were a couple of things from the carbohydrates chapter. One concept there that we didn't quite describe in class that's important, and another concept or another illustration of terpene chemistry from the lipids chapter that's important. So this will probably take anywhere between 15 and 20 minutes, and I'm sorry to have it be out of order, but just wanted to make sure you had that information. So in the carbohydrates chapter, we talked about the beta anomer of glucose, of beta D glucopyranose, which has the OH at carbon 1 in an up equatorial position when you draw the molecule this way. This is the beta anomer. And then we also drew the alpha anomer, which is when the OH at carbon 1 is down axial when the glucopyranose is drawn this way. This is the alpha anomer. And there was a point in the lecture on carbohydrates where I hedged a little and would sometimes draw a carbohydrate like this, where I would use a squiggly line at the anomeric carbon to indicate a mixture of alpha and beta anomers. Why would I do that? It turns out that under some conditions, the alpha and the beta anomers can equilibrate. So if you want to communicate a mixture of alpha and beta anomers, you can either use the squiggly line or you can draw both of them, and there are ways you can determine what ratio of alpha and beta anomers you have. But I want to just talk briefly about this process whereby the alpha and beta anomers interconvert. This process has a name. It is called mutarotation. Mutarotation in the sense that it's a not really rotation. You can't get from the alpha to the beta anomer and vice versa by rotating around any carbon-carbon bonds. But mutarotation can happen via a couple of different ways, and they all have to do with acetal formation. So let me show you one way that we can interchange between the alpha and the beta anomers, and then I'll show you another way, and then we'll move on. If we protonate the OH group on carbon 1, I'm not showing you that mechanistically, because I can imagine you knowing how to draw that proton transfer. Then that turns the OH into a good leaving group. Then electrons on the nearby neutral oxygen can kick down and kick off water as a leaving group. And that will generate this oxonium ion. May be helpful here to draw in the hydrogen that's implied but not shown. And you can see now that if water were to attack this oxonium ion from the top face, we would go right back to this protonated beta anomer. But if it attacked from the bottom face, we would go back to, we would instead get the protonated form of the alpha anomer, which of course we could then, I'm just going to write deprotonate at the anomeric OH to give us our anomer. our alpha anomer. So that's one way by which we can interchange alpha versus beta anomers. The other way is actually by open chain, by getting to the open chain form. So if I start with the beta anomer, and if instead I were to protonate on the ring oxygen, that would turn this ring oxygen into a good leaving group, and electrons on the OH at carbon 1 could kick down and kick off that leaving group. That would get us to the following open chain form. These mechanistic steps should not be a surprise. You should see them as variations on hemiacetal formation, acetal formation, hemiacetal hydrolysis, acetal hydrolysis, and so on. When we get to this open chain form, we are now perfectly able to rotate around that carbon-carbon bond, and imagine rotating around it such that the open chain form now, oops, didn't mean to erase all of that, such that the open chain form now looks like this, with the hydrogen pointed this way and the oxonium ion pointed that way. Then attack of the ring oxygen on the oxonium ion generates, recloses up the ring and generates this intermediate, and then deprotonate the ring oxygen, gets you to the alpha anomer. So there are sort of two different ways you can talk about mutarotation. One just involves loss of water and attack from the other side. The other involves ring opening, rotation around a carbon-carbon bond to change the conformation, and then closing up to get the alpha anomer. So the alpha and the beta anomers are in equilibrium with each other. Now there's more we could say on that subject about the relative stability of the alpha versus the beta anomers. I'm going to skip that. That's an important subject to me and to organic chemists in general, but we're just going to skip it because we have some other important things to talk about. All right. So, and also in addition to mutarotation, be aware that some carbohydrates have replacements of some of the of one of the OH groups with a nitrogen. So, for example, this is glucosamine in its pyranose form. We're replacing the OH on carbon 2 with an amino group. And glucosamine you will have heard of before. Some people take it as a nutritional supplement. It has various uses biologically, sometimes found in the components of the extracellular matrix. Sometimes that nitrogen of the amino group is tied up in an amide bond with an acetyl group. The nitrogen gets acetylated, and that generates this carbohydrate, which is sometimes called N-acetylglucosamine. And N-acetylglucosamine is an important component of chitin, which is a very rigid carbohydrate. All right, That's all we have time for on carbohydrates. I now want to return our attention to terpene chemistry. And last time we were talking about how the very interesting structures can be built up from relatively simple precursors. So our precursor, geranyl pyrophosphate, looks like this, and I'm abbreviating the pyrophosphate leaving group as shown here. Sorry, I meant to just do 2 isoprene units. Here is, oops, that's an eraser, not a highlighter. There's the purple one, and here's the orange one that we talked about last time. And I want to show you how biology elongates a linear terpene, geranyl pyrophosphate, or geranyl diphosphate, to a longer derivative with 1 additional isoprene unit. And this will actually show you how to get the starting material for the cedarol synthesis that we talked about last time. And the product of this reaction is going to connect the green isoprene unit with the orange isoprene unit in one of these classic head to tail linkages. Where this is the green isoprene unit and orange 5 is bonded to green 1. How this works is essentially you need the 2 isoprene unit precursor, geranyl pyrophosphate, and then you need this other precursor, isopentenyl pyrophosphate. And it's the synthesis of this shorter isoprene unit that and a close relative called dimethyl allyl pyrophosphate that is the target of statin drugs. Statin drugs lower your cholesterol by slowing down the synthesis of this precursor. We'll show you actually the connection between these precursors and things that look like cholesterol in the next few minutes. But we're going to react isopentenyl pyrophosphate with geranyl pyrophosphate to get farnesyl pyrophosphate. And the mechanism is going to be relatively simple. The allylic good leaving group is going to leave to give me a resonance stabilized allylic carbocation. Then isopentenyl pyrophosphate is going to act as a nucleophile. We're going to do again, so the first step was sort of SN1 style leaving group leaves. The next step is going to be regioselective addition of an electrophile to an alkene in a way that gives us the new bond. Here in red is the new bond we just made. We selectively make the bond between orange 5 and green 1 so that the positive charge can be on green 2 where it is more stable. And then the final step to get to farnesyl pyrophosphate basically consists in an E1-like elimination step, a base either from solvent or within the enzyme removes the proton that's adjacent to the positive charge, and we do elimination chemistry. That puts the new pi bond here between 2 and 4. The reason we want the pi bond between 2 and 4 is if it's there, now the next leaving group can be in the allylic position. You get selectivity to have the double bond between 2 and 4 driven presumably by the enzyme. So this is, adding on of an additional terpene unit, additional isoprene unit, and there are other natural products that come from addition of other isoprene units on in sort of this, what I'm going to call head to tail or tail to head terpene elongation. Now that's actually not any more difficult than you've done before. You should hopefully be able to see how you could take something like this precursor, dimethyl allyl pyrophosphate, and then that other isopentenyl pyrophosphate, and use those together through the same sequence of types of reactions to generate geranyl pyrophosphate. Okay, you've seen some of what biology is able to do. Last time as we talked about terpenes, I now want to show you how nature can take farnesyl pyrophosphate and get the kinds of complicated structures that are present in the steroid hormones and steroid-derived molecules. Some of these steps we will not discuss the mechanism of. Others are going to involve basic terpene steps that you should be familiar with, and you should be able to understand the regioselectivity of these various steps. So, as context, nature will begin with 2 subunits of farnesyl pyrophosphate. And through a reaction that we won't talk about, chemists have worked out a lot of the details of this reaction. Nevertheless, it's sort of beyond the scope of an introductory OChem class. I'll show you what this reaction does without commenting on the mechanism. I'm going to highlight the isoprene units that are present in this product in this starting material. I'm also going to highlight the bonds between isoprene units that were present in these linear precursors. So you get 2 of these, and nature actually uses an enzyme called squalene synthase, and you actually also need a reducing agent. This reaction is formally a reduction. If you look, you'll be able to see the number of carbon heteroatom bonds decreasing as we undergo this process. And the process basically takes 2 farnesyl pyrophosphates and links them together in an unusual head-to-head fashion. Normally, terpenes are linked together in head-to-tail fashion, such that the carbon number 5 of one isoprene unit is connected to carbon number 1 of the other isoprene unit. But if you watch at the connection between the pink and the green isoprene units, you can see that it's carbon 5 of the green isoprene unit that's linked to carbon 5 of the pink isoprene unit. This is an unusual head-to-head elongation, and you don't need to worry about the details about how that happens. But it's important for setting up the study, or setting up the approach to the much longer or the much more complicated steroid hormones, because this is how we generate squalene, which is a triterpene. It has 6 isoprene units, which means it's got 30 carbons. And just to give you a preview of where we're going, when we're done, you will see how these 30 carbons become converted to the following much more complicated system. It's almost mind-blowing that biology is able to do this. Okay, so, and the question is, how does that happen? Well, so this is our goal. If you count the number of carbons, though, there's 30 carbons there. So all of those carbons were initially put in place through this linear terpene precursor. So the first step is that nature does a reaction where it uses oxygen and the cofactor FAD and an enzyme called squalene monooxygenase to make an epoxide in the purple isoprene subunit. And that puts the oxygen right there. So we've turned that terminal isoprene unit into an epoxide. What happens next is easier to see if I redraw the squalene molecule. Okay, sorry, I skipped ahead and redrew squalene in a squalene epoxide in a slightly different way that will help you see what happens next. First, the squalene epoxide oxygen gets protonated to give you this oxonium ion. So what we've got here is a regioselective epoxide opening problem. The question is, for an epoxide, which of the 2 carbons should be attacked by a nucleophile? Should it be carbon 2 or carbon 4? And the answer is, of course, for protonated epoxides, that we prefer attack at the more substituted carbon, where a buildup of positive charge is more stable. What is the nucleophile going to do the attacking? Well, it's this carbon-carbon bond, which is ideally positioned to attack the epoxide as a nucleophile via backside attack. How's that going to happen? Which of these 2 atoms involved in that pi bond is going to get the new bond with purple carbon 2? The answer is it should be 4, because that would make a 6-membered, it should be orange 4. That's because that would make a 6-membered ring, and because it would lead to a buildup of partial positive charge on carbon 2 where it's more stable. So we've got backside attack of the pi bond on the electrophile. That's going to make a new a new sigma bond between orange 4 and purple 2. At the same time, we're going to build up partial positive charge on carbon 2 where it's more stable. But look what we have 6 spaces away on green carbon 4. Between green carbon 4 and green carbon 2, we have this pi bond, which can again act as a nucleophile to attack the building up of positive charge on orange 2, which happens at the same time as orange 4 is attacking purple 2. Do you see how the placement of the pi bonds at this sort of regular interval creates a situation where when we open up the epoxide, we put positive charge there, and then this double bond is poised to attack. Again, the new bond should be between green 4 and orange 2, so that there can be a buildup of partial positive charge on orange 2, where it will be more stable. And a few atoms away, we also have the pi bond between pink 2 and pink 4. 1, 2, 3, 4, 5. If pink 2 attacks the building up a positive charge on green 2, we get a 6-membered ring, but a positive charge on a partial positive charge on less substituted carbon 4. If the pi bond attacks such that we form a new bond between pink 4 and green 2, we get a 5-membered ring, but the positive charge gets to build up on more substituted carbon 2. The result from biology is that it's more favorable for the pi bond to create a new bond between pink 2 and green 2, such that we form a 6-membered ring, and then that would lead to a buildup of partial positive charge on carbon 4. And then again, we have a carefully placed nucleophile between blue 2 and blue 4 that's ready to attack. And apparently for this ring size, it's preferable to form the new sigma bond between blue 4 and pink 4, such that we make a 5-membered ring and there can be positive charge on carbon 2. And that's where this cyclization cascade ends. It's actually an interesting question whether these all occur in the same concerted step like this, or whether they occur via discrete intermediates, an energy landscape like this, or whether the potential energy surface is long and broad with not a lot of variation in energy between transition states and intermediates. There are people that look into that. We're going to draw them all at once so that we don't end up having to copy and paste forever. I'm going to show you where the new bonds end up. And as we do, then we're going to draw this molecule from a different perspective. So we break the bond between the carbon 2 and the epoxide. I'm going to swing this methyl group up in this direction, and then in blue I'm going to show the new bond we make between purple subunit, isoprene subunit, purple carbon 2 and orange carbon 4. Then we'll illustrate the new bond that we make between green 4 and orange 2. Here, that's a 6-membered ring. Then I'm going to illustrate the new bond we make between green 2 and orange 2. That's a new 6-membered ring. Then I'm going to illustrate the bond that we make between blue 4 and pink 4. that would be here. So we make 1, 2, 3, 1, 2, 3, 4 bonds. And this one, which I've kept blue, was from the maybe we'll make it gray, the head-to-head cycles, the head-to-head elongation of 2 farnesyl pyrophosphates to form squalene. All right, so if we follow that through and look at what we've just made, it looks like this. Where the isoprene units are as follows. Here's my purple. Here's orange. Here's green. Here's pink. Here's blue. And then here's gray. Here are the individual bonds in red that were present in the linear precursor. Except we're using gray for the bond between green and pink subunits. And then in blue are the new bonds we made in the cyclization process. This intermediate is called a protosterol cation, and I'm not showing you the process for converting that protosterol cation from the cation to lanosterol, though this involves a bunch of 1,2-methyl and 1,2-hydride shifts. See if you can work it out, followed by an E1 style elimination step to remove a proton that's adjacent to a carbocation to get the double bond in place. All right, so that's just an example of terpene chemistry. I'm skipping the carbocation rearrangement because I don't want this to take longer than it already has. We've already spent maybe 10 minutes longer on this than I intended to. But this lanosterol is a precursor. There are 19 more biosynthetic steps between this and cholesterol, which is a precursor for various hormones and bile salts and other types of things. Also from cholesterol, you can make vitamin D or vitamin D3. So it's an interesting example of lots of complexity built up from relatively simple starting materials. It also gives you a clue as to what statin drugs do. They're supposed to lower your cholesterol, but the way they do that is way, way, way back here. They inhibit the syntheses of dimethyl allyl pyrophosphate and isopentenyl pyrophosphate. Okay, with that, it's time to move on to the nucleic acids in chapter 26. There's a lot to be talked about in chapter 26, and a lot of it is going to involve facts and structures. There are structures I want you to know. I want you to know the structures of the nucleobases. I want you to know the structures of nucleosides versus nucleotides. And I want you to know their names as well. So we'll go through these. These are things that you'll learn. You'll need to memorize them. You'll learn them again in biochemistry, and hopefully they will stick with you. I found it useful to group the nucleobases into two sort of categories, and they're named according to the kind of heterocyclic rings that are present. The purines have this weird sort of fused 5 and 6 membered ring structure. So the purines include adenine. Here's the 5-membered ring of adenine. This nitrogen is the one that's attached to the ribose ring. If it were just adenine, on the other side of the squiggly line would be a proton. If this is attached to the ribose ring, this would be one of the carbons of ribose. So there's the 5-membered ring, and then here is the 6-membered ring. This has the abbreviation A, and a couple of interesting features. This nitrogen is often called an exocyclic amino group because it's outside the heterocyclic ring. The other thing that can be useful is to distinguish the groups that are within the ring, especially the heteroatoms, as being a hydrogen bond donor. That is, does it have an electron poor NH bond that it can use for hydrogen bonding versus a hydrogen bond acceptor. Hydrogen bond acceptors are basically going to be lone pairs on electronegative heteroatoms. So I'm going to highlight in the structure of adenine the hydrogen bond acceptors in blue and the hydrogen bond donors in pink. The exocyclic amino group is a hydrogen bond donor. The ring nitrogens with sp2 hybridized lone pairs are hydrogen bond acceptors. And it's these ones on the right, the exocyclic amino group, and then this nitrogen, this first nitrogen, that are involved in Watson-Crick type base pairing. Also on the list of purines is another structure called guanine. Abbreviated G. This shares some of the structural features of adenine. The 5-membered ring is exactly the same, but the 6-membered ring is not. It has the nitrogens within the ring in the same place, but the other details are dramatically different. Notice that guanine also has an exocyclic amino group, but it's in a different spot. And notice that the pattern of hydrogen bond donors versus acceptors is different for guanine versus adenine. Whereas adenine had donor acceptor, guanine has acceptor donor donor. And that pattern is different. Similarly, you can expect 2 hydrogen bonds in a Watson-Crick base pair involving adenine and 3 in a Watson-Crick base pair involving guanine. All right, with that in mind, we should also talk about the second class of nucleobases, which are called pyrimidines, not to be confused with pyridine. Pyrimidines are 6-membered rings with 2 nitrogens in them. And there are three common pyrimidine bases, though really two of them are really quite similar, and one's in DNA and one's in RNA. So we'll start with uracil, one letter code U, and uracil is found in RNA. Uracil looks like this. We'll put the nitrogen at the bottom of the ring. This squiggly line indicates what would be the attachment point to the ribose ring. And then in uracil, everything else is like this. So you can see that we have a hydrogen bond donor there, and then hydrogen bond acceptors there. Thymine is the DNA equivalent of uracil, and thymine differs from uracil only in the presence of a methyl group at that carbon. Of course, as you know, thymine forms Watson-Crick base pairs with adenine. Uracil forms Watson-Crick base pairs with adenine. And then guanine forms a Watson-Crick base pair with the last of the bases, which is called cytosine. This last of the bases is, I think, kind of named in a way that's unfortunate. And the reason for that is, in a lot of cases, in most of the cases, especially for adenine and guanine, though the name adenine and guanine is for the base, when the base is attached to a ribose ring, you add the ose in between. So this attached to a ribose ring would be adenosine, but not for cytosine. So it's kind of confusing in that way. I didn't make it up, and it's too late to do anything about it. So cytosine has the same six-membered ring structure with the nitrogens in the same relative orientation with respect to each other. Cytosine also has an exocyclic amino group, and the pattern of hydrogen bond donors versus acceptors on cytosine is donor, acceptor, acceptor. Notice that that's complementary to what you expect for guanine. Acceptor, donor, 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 acceptor, acceptor, which is why C and G engage in favorable Watson-Crick base pairing. All right. While we're on the subject, let's just show you the complementary base pairing between guanine and cytosine, and between adenine and uracil, or adenine and thymine. All right, so here's an adenine, only here we're gonna draw out at least one of the NH bonds. And then let's show the hydrogen bonds in gray. So I drew some of the ends sideways, which was not my intent. Sorry, I don't like how I drew that at all. I guess I'll try that again. Gosh. All right, so this is a Watson-Crick base pair between uracil and adenine. And you can see there are two hydrogen bonds between the exocyclic amino group of adenine and the carbonyl oxygen of uracil, and then between the ring NH of uracil and one of the ring nitrogens of adenine. And of course, if this were thymine, we would just add a methyl group here. And then let's show you the Watson-Crick base pair between guanine and cytosine. I'm going to just erase briefly the exocyclic amino group. And we'll show hydrogen bonds here and here and here. And then you can sort of imagine what's going to happen. As donor on cytosine interacts with acceptor on guanine and vice versa. And notice that each GC pair has 3 hydrogen bonds. And it's also true that from end to end, an AT or AU base pair takes up about the same space as a GC base pair, such that these individual base pairs can stack over each other in DNA. So this is an example of Watson-Crick base pairing. There's other kinds of base pairing, alternatives to Watson-Crick base pairing that aren't mentioned in your text, and we unfortunately don't have time to talk about. All right, I want to give you a little bit more nucleic acid nomenclature before we dive into DNA structure. And so let's talk about ribonucleotide, or rather, let's talk about adding these bases to the sugars. So if you have a nucleobase plus a ribose sugar, that's called a nucleoside. Here is the structure of ribose. It's a 5-membered ring. Both, and the atoms of the ring are numbered 1 prime, 2 prime, 3 prime, 4 prime, and then there's a hydroxy methyl group 5 prime and an OH on the 5 prime hydroxy Sorry, got a little bit carried away with the drawing. It should be a wedge here. It's a 5' hydroxy group. And then also a wedge at carbon 1 is the nitrogen of one of these bases. Let's just go ahead and make it the nitrogen of adenine. And remember, adenine's got the exocyclic amino group up here. So you've got the adenine base. You've got the ribose ring, the ribose sugar. Let's highlight the ribose sugar in orange. Let's highlight the adenine base in green. You put them together and it is a nucleoside which has the name adenosine. I will point out that this bond between the nitrogen and the anomeric carbon of the sugar, that's called an N-glycosidic linkage. And nucleosides are an example of what are called N-glycosides. The anomeric carbon of the ribose ring is making a bond with the N, the nitrogen of the base. Okay, so let's talk about what the names are of the nucleosides when the base is A. We've already said it's adenosine. If it's G, it's guanosine. That sort of makes sense because you're sort of combining the name adenine with the name ribose. And it only makes sense for the purine nucleosides. For the pyrimidine nucleosides, it's a little bit weirder and you just have to get used to it. For uracil, the nucleoside is called uridine. For thymine, the nucleoside is called thymidine. And for cytosine, the nucleoside is called cytidine. And again, I don't know why. You can think of lots better ways to do this. But those are the names and they're not changing. I will say that these are called ribonucleosides because this ring is ribose. Ribose has oxygens on the 2' and 3' positions of the ring. Of course, ribonucleosides are different from their DNA-related cousins. So whatever we've said here, we can copy here. In DNA, the 2' hydroxyl is missing. So these are called deoxyribonucleosides, and you would call this particular deoxyadenosine. So to name each of the nucleosides, you would use deoxy. You would put the prefix deoxy ahead of adenosine and guanosine and uridine and thymidine and cytidine. And you would also, if you want to abbreviate these nucleosides, you would also place a lowercase d in front of the letter. Okay, So those are ribonucleosides and deoxyribonucleosides. What we want to talk about next are what are nucleotides. So a nucleotide is you have the nucleoside, but we're going to add phosphoesters or add phosphate groups. Okay. And there's a lot of different ways that you could do this, but let's give you some examples. We'll copy the structure of our adenosine nucleoside, and then we're going to take the 5' hydroxyl group and we're going to modify it with a phosphate group. There are 3 different hydroxyl groups in adenosine that could have the phosphate, and so our name for this needs to account for that. The name for this is adenosine 5' monophosphate. But you will see this abbreviated in biochemistry as AMP. The first phosphate group on, shoot, I want to make sure I don't get that one wrong. Got to check it out. Well, the first phosphate group on DNA, or sorry, the first phosphate group is sometimes given the Greek letter alpha, and if we add additional phosphate groups, they can be given the Greek letters beta and gamma. All right, so this would be adenosine monophosphate, and that is an example of a nucleotide. Of course, we could continue on adding additional phosphate groups, and we'll start to get some molecules that you are, maybe somewhat familiar with. For example, if we modify that phosphate on adenosine monophosphate with another phosphate group to make a phosphoanhydride linkage, this then becomes adenosine, not monophosphate, but diphosphate, or ADP. It's still a nucleotide. Or if we had 3, that would then become adenosine 5' triphosphate, or ATP for short. Okay, so that's a lot about nomenclature of nucleotides versus nucleosides versus nucleobases. What I've said for the ribonucleotides that are made from ribose rings is the same as what I would say for deoxyribonucleotides. So, for example, we could take this ATP, and if we remove the 2' hydroxyl, sorry that the orange went away. If we remove the 2' hydroxyl, we now have a deoxyribonucleotide, and that would be called deoxyadenosine 5' triphosphate, or DATP. All right, so that's your survey of nucleic acid structure. What we want to do next is talk about nucleic acid, the synthesis of polymers of these individual nucleotides. and that will get us into talking about DNA structure and function.